fabulous French restaurant. Et voilà, voilà. Et voilà. Ah, une bouteille de vin. Oui, oui. Une serviette. No, no, what is this? What's a plate? J'ai oublié. What? Okay. What?
Oh my God.
A which? Serviette. Is it okay? I know. No, it's a napkin then. Anyway, all right. Wait. Before we go to the restaurant, though, let me show you one of my favorites. Watch this. Watch. Excuse me. Watch. One of my favorites. Watch this. I can pull this piece of paper out from in there, and they stay standing. Watch. Oh, dang it. How do I have to do it? Do it fast? You mean like that? Yeah. How fast? Like that? Okay. Huh? All right. All right. Are we ready? Da 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 da. And the bottle is still standing. Da 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 da. All right. Oui, but it's not enough. It is not enough. We must have une bouteille de vin et un arbre de Noël, un petit homme japonois, les candles. Oui. I don't know how to say candle in French. Ah, oui, monsieur. Oui. Je pense, oui. Oh, they should go there. Really? Huh? A little tree. Une grande bouteille. Oui. Oh, what could go wrong? And the flowers are still standing. I should stop while I am ahead, but I will not. All right. I will not stop until... Okay, one of the times when I did this, right, I had a bottle that fell, and there was like the floor was right there, right? So it just fell. I cut timber right onto the concrete floor, just smithereens. You should have seen the kid's eyes, too. All right, let's see. Oui, bonbon. Oh, whoa. Oui, bonbon. All right. Oh. You guys have to have like glass things, right? Oui. Okay, now, it's important to have hearing protection when you do something like this, right? Because, if a bottle does fall and a student is seriously injured, right? No, I just don't want, to be deafened by the screaming, of the injured student. All right. What could go wrong? Yeah! Woo! Okay, watch this. No, just kidding. Reese Thomas could do that. Reese Thomas could pull that middle bottle out and then reach down, grab the bottom one. Do you guys know of whom I'm talking? He is our juggler, like Portland's remarkable juggler. He will come to Tualatin High School and be in the auditorium May 29th. Free show. Well, free to you guys. What? It's going to be in the evening. It's going to be in the evening. A little more applause for the French restaurant. Ristorante. Oh yeah. Yeah, we should do that after the. Okay. Okay, I think we've done the heck out of the first law. Okay, the second law is where we're going to go as far as like problem solving and stuff. Almost all our problem solving will be done with, well, I think all of it will be with the second law. The second law just states that if there is an outside force and it's unbalanced, unbalanced outside forces cause an acceleration. So I'm going to write unbalanced outside forces cause an acceleration. And that acceleration is equal to the force divided by the mass. This is Murray's way of writing it. Yeah. Unbalanced forces, outside forces, cause an acceleration. They must cause an acceleration. And that acceleration is equal to the force divided by the mass. Now, of course, Newton's second law is just a formula, F equals ma. And we can make a little triangle here, right? We can go F and M and A for the mathematically impaired. So acceleration is F divided by M. Mass is force divided by acceleration. And force is mass times acceleration, right? But this is a good way to think about it, and it makes sense, right? The more force you exert, the bigger the acceleration. What about the more mass? If we have more mass, what happens to the acceleration? It gets less acceleration, right? It'll accelerate, but just not as much, right? So the bigger the mass, the less the acceleration, right? The bigger the force, the bigger the acceleration. Okay? So another way of saying this is, how do we talk about inertia? Well, inertia is mass, right? Okay? And our unit of mass, our physics unit of mass, is a kilogram. Okay? We are going to use mass in kilograms, right? Acceleration is going to be meters per second squared. And then if we have a force such that will accelerate 5 kilograms, let's just say, for example, at 4 meters per second squared, right? Then that's a force of 20 kilogram meters per second squared. That's actually 20 newtons after Sir Isaac, right? So you can say 20 capital N, like that. Okay. So we have another unit of force. A kilogram meter per second squared is a newton. It's a newton. It's a newton, and we're going to spend the rest of the period sort of on that, you know. She turned me into a newton. So when we talk about inertia, by the way, inertia is proportional to the mass. Double the mass, double the inertia, right? And acceleration is the rate change of motion, yes? Okay? And then the final law, and this is a crazy law, okay? For every action, there's an equal but opposite reaction. Do we know this one? We know this one, don't we? Okay? What this means, it means, a lot of people like to, make up what it means, but it means specifically that if you were floating in space, I'd love to have a place where we could just sort of all float, like turn off gravity. Wouldn't that be fun? Like one of these switches.